So now we have conversion of cyclobutene to 1,3-butadiene by Kahn rotation, in which C2 axis of symmetry maintained. So here we have to write the symmetry properties of the 4 molecular orbitals of cyclobutene on this side. So sigma, pi star and sigma star, and their symmetry properties with respect to C2 axis of symmetry. This is Kahn rotation, in which C2 axis of symmetry is maintained. So Kahn rotation, in which C2 axis of symmetry is maintained. We have to write the symmetry properties of the directly involved orbitals of cyclobutene with respect to C2 axis of symmetry on one side, and on the other side we write the symmetry properties of the 4 molecular orbitals of 1,3-butadiene, Psi1, Psi2, Psi3 and Psi4, and their symmetry properties with respect to C2 axis of symmetry. Now join various orbitals of the reactants and products by lines having same symmetry property. Here Psi1 can correlate with Psi1 cannot correlate with sigma because Psi1 is anti-symmetric and sigma is symmetric. Therefore, this Psi1 which is anti-symmetric correlates with pi only. It cannot correlate with this sigma. So psi1 square correlates with pi square, and psi2 square correlates with sigma square. Square indicates 2 electrons. So ground state orbitals of 1,3-butadiene correlate with ground state orbitals of cyclobutene. So in the ground state orbitals of reactants correlate with ground state orbitals of the product, the reaction is thermally allowed. So here the ground state orbitals of cyclobutene, sigma square and pi square correlates with the ground state orbitals of the products, psi1 square and psi2 square. Therefore, this reaction is thermally allowed. So conversion of cyclobutene to 1,3-butadiene by Kahn rotation, in which C2 axis of symmetry is maintained, is thermally allowed. Similarly, this is photochemically forbidden because the first excited state, that is the first excited state of cyclobutene, is sigma square pi and pi star. The sigma square pi and pi star, it cannot correlate with first excited state of the 1,3-butadiene, psi1 square, psi2 and psi3. So psi1 square is correlating with pi, psi2 is correlating with sigma square, but psi3 is not correlating with pi star. Psi3 is correlating with sigma star. Pi star is not correlating with psi3. It is correlating with psi4. That means the first excited state of the product does not correlate with first excited state of reactants. Therefore, reaction is photochemically forbidden. So therefore, Kahn rotation in which C2 axis of symmetry is maintained is thermally allowed and photochemically forbidden. So in this case, the ground state orbitals of cyclobutene, sigma square and pi square correlates with psi1 square and psi2 square. When the ground state orbitals of the reactants correlate with ground state orbitals of the product, the reaction is thermally allowed and photochemically forbidden. So conversion of cyclobutene to 1,3-butadiene by Kahn rotation, in which C2 axis of symmetry is maintained is thermally allowed and photochemically forbidden. That is how we have to draw the correlation diagrams for Kohn rotation in which C2 axis of symmetry is maintained. When we consider Kohn rotation, we have to take the symmetry properties of the directly involved orbitals of the reactants and products with respect to C2 axis of symmetry. So these are the 4 pi electron systems. Next we go to the 6 pi electron systems. 6 pi electron systems. So conversion of cyclohexadiene to hexatriene. A ring opening. This is electrocyclic ring opening reaction. So we can take ring closure or ring opening. From cyclohexadiene to 135 hexatriene, it is electrocyclic ring opening. So reverse reaction is 135 hexatriene to cyclohexadiene. This is electrocyclic ring closure. So in an electrocyclic reaction, one pi bond is converted into one sigma bond. So two pi bonds move from one position to other position, and one pi bond is converted into a sigma bond in the product. That is electrocyclic reaction. So if the acyclic compound contains 4n pi electrons, cyclic product contains 4n minus 2 pi electrons with one additional sigma bond. That is an electrocyclic reaction. So now let us draw the correlation diagrams for this. Let us see how to draw the correlation diagrams for this. We have to take 6 molecular orbitals psi1, psi2, psi3, psi4, psi5 and psi6 of 135 hexatriene. So we have to consider 6 molecular orbitals from psi1 to or 135 hexatriene, and in the case of cyclohexadiene we have to consider this sigma bond which is newly formed and these two pi bonds. This is one pi bond and this is another pi bond which have shifted from one position to other position. So consider two pi orbitals and one sigma orbital in the case of cyclohexadiene, and then apply Kohn rotation and disrotation. When we apply disrotation, we have to take the symmetry properties of the molecular orbitals with respect to the mirror plane symmetry. And when we apply Kohn rotation, we have to take the symmetry properties of the orbitals with respect to C2 axis of symmetry. So first we have considered here a disrotation in which mirror plane symmetry is maintained. So here we write the 6 molecular orbitals of cyclohexadiene. Sigma, phi1, phi2, these are bonding orbitals, phi2 square, phi1 square, phi2 star, phi1 star and sigma star. These are anti-bonding molecular orbitals of the cyclohexadiene, and these are symmetry properties of these 6 molecular orbitals with respect to the mirror plane symmetry. So on this side we consider 6 molecular orbitals of the 135 hexatriene, psi1, psi2, psi3 bonding, psi4, psi5, psi6 anti-bonding. These are the symmetry properties of these orbitals with respect to mirror plane symmetry. So now to draw this correlation diagram and see the conservation of orbital symmetry, we join the orbitals having same symmetry properties. So sigma square correlates with psi1 square. So sigma square correlates with psi1 square. So pi1 square correlates with psi2 square. Pi1 square correlates with psi3 square. And phi2 square correlates with psi2 square. So psi1 square correlates with sigma square Psi2
Sigma.
square correlates with pi2 square. Psi3 square correlates with pi1 square. So in other words, what we can say, the ground state orbitals of 135 hexatriene correlates with ground state orbitals of cyclohexadiene. Therefore, this rotation in which mirror plane symmetry is maintained is thermally allowed because the ground state orbitals of reactants correlate with ground state orbitals of the product. Therefore, conversion of cyclohexadiene to 135 hexatriene by disrotation in mirror plane symmetry is maintained is thermally allowed. Similarly, it is photochemically forbidden because the first excited state of the cyclohexadiene is sigma square, pi1 square, pi2 and pi2 star, and it does not correlate with psi1 square, psi2 square, psi3 and psi4. So bonding orbitals are correlating, but anti-bonding orbital psi4 is not correlating with pi2 star. Pi4 is correlating with pi1 star. Similarly, pi2 star is not correlating with psi4. It is correlating with psi5. Therefore, the first excited state of the cyclohexadiene does not correlate with first excited state of 135 hexatriene. Therefore, the reaction is photochemically forbidden. So, therefore, this rotation is thermally allowed and photochemically forbidden. Now, we take con rotation. So, here you can see psi1 square, psi2 square, psi3 square correlates with sigma square, pi1 square, pi2 square. That means the ground state orbitals of the reactant correlate with ground state orbitals of the product. Therefore, the reaction is thermally allowed. Similarly, the first excited state of the reactant, sigma square, pi1 square, pi2 and pi star is correlating with higher excited state. It is not correlating with psi1 square, psi2 square, psi3 and psi4. So therefore, the first excited state of reactants is not correlating with first excited state of products. Therefore, this reaction is photochemically forbidden. Next, we take the con rotation. So conversion of cyclohexadiene to 135 hexatriene by con rotation, in which C2 axis of symmetry is maintained. This is con rotation in which C2 axis of symmetry is maintained. So same conversion of cyclohexadiene to 135 hexatriene by con rotation in which C2 axis of symmetry is maintained. These are 6 molecular orbitals of cyclohexadiene. So sigma square, pi1 square, pi2 square, pi2 star, pi1 star, sigma star. And on this side we have 6 molecular orbitals of the 135 hexatriene, psi1, psi2, psi3, psi4, psi5 and psi6, and these are symmetry properties with respect to the C2 axis of symmetry. And here also we have written symmetry properties of the orbitals with respect to C2 axis of symmetry. So sigma is symmetry, pi1 is anti-symmetry, pi2 is symmetry, pi2 star is anti-symmetry, pi1 star is symmetry, sigma star is anti-symmetry. And here psi1 anti-symmetric, psi2 symmetric, psi3 anti-symmetric, psi4 symmetric, psi5 anti-symmetric, psi6 symmetric. So now try to join orbitals having same symmetry properties. So we can join orbitals having same symmetry properties. So this psi1 square correlates with pi1 square. So psi2 square correlates with sigma square. So psi3 square does not correlate with pi2 square. Psi3 square is correlating with pi2 star. It is not correlating. Psi3 is not correlating with pi2. Similarly, psi4 is not correlating with this pi2 star. It is correlating with pi2. So that means here the ground state orbitals of the product does not correlate with ground state orbitals of the reactant. Therefore, this reaction is thermally forbidden. When the ground state orbitals of the reactant does not correlate with ground state orbitals of the product, the reaction is thermally forbidden. But here, the first excited state of cyclohexadiene, sigma square, pi 1 square, pi 2 and pi 2 star correlates with first excited state of hexatriene, that is psi 1 square, psi 2 square, psi 3 and psi 4. So first excited state of products correlates with first excited state of reactants. Therefore, Kohn rotation in which C2 axis of symmetry is maintained is photochemically allowed and thermally forbidden, because here ground state orbitals of reactants does not correlate with ground state orbitals of product, but the first excited state of the reactant can correlate with first excited state of the product. Here we can psi 1 square, psi 2 square, psi 3 square does not correlate with sigma square, pi 1 square, pi 2 square. But the first excited state, psi 1 square, psi 2 square, psi 3 and psi 4 can correlate with sigma square, pi 1 square, pi 2 and pi 2 star. Therefore, conversion of cyclohexadiene to 135 hexatriene by Kohn rotation in which the two axis of symmetry is maintained is photochemically allowed and thermally forbidden. This is these are the correlation diagrams for electrocyclic reactions. So earlier we have already seen the correlation diagrams for cycloadditions. While taking cycloaddition, while drawing correlation diagrams for cycloadditions, for this 6 pi electron system, we have to write the symmetry properties with respect to vertical plane of symmetry. This is Diels-Alder reaction, 4s plus 2s cycloaddition. This type of system has only vertical plane of symmetry. Here we will not take mirror plane symmetry and C2 axis of symmetry. In this case, in the case of cycloaddition, we have to write the symmetry properties of directly involved orbitals of reactants and products only with respect to vertical plane. This type of type cycloaddition has only vertical plane of symmetry. Whereas if we consider 2s plus 2s cycloaddition, we have both vertical and horizontal planes of symmetry. So before drawing correlation diagrams, here we have to write the symmetry properties of the orbitals with respect to first vertical plane and then horizontal plane. So this is vertical plane and this is horizontal plane. So this 2s plus 2s cycloaddition has vertical plane of symmetry and also horizontal plane of symmetry. So we write the symmetry properties of the orbitals here with respect to vertical plane and horizontal plane. And this we have already seen the construction of correlation diagrams for this. This reaction is thermally forbidden, photochemically allowed. And then we have seen this, there are no correlation diagrams for sigmatropic reactions. We have correlation diagrams for electrocyclic reactions and cycloaddition reactions only. And after that, we have seen this Huckel's rule of aromatic and anti-aromatic transition state observation.